Okay, so section 3.4, let's just jump right into it. So we're going to talk about, we kind of touched on it last time. Last time we touched on something called a z-score, and now we're going to maybe expound on it a little bit. Last time we said, well, we want to know how many standard deviations a value is away from its own mean. That's actually exactly what a z-score is. If you have a data value, x, you would subtract off the mean of, let's say, the population and divide by the standard deviation. And that's going to tell you how many standard deviations you're going to be away from the mean and which direction. If your z-score is negative, a negative z-score means that that data value would have been less than the mean, below the mean. If your z-score is positive, that means your data value was above the mean or greater than the mean. If your z-score happens to be exactly 0, that means that data value happens to be equal to the mean. But that's just a coincidence. That doesn't always mean anything special. It doesn't always signify something cool. I guess technically you can do a sample z-score and you just replace the population statistics with sample statistics. We're not ever really going to have to worry about that. We're not going to get into that level of detail with it. Let me close the door real quick. So, let's see what's going on here. Z-score, take your x value, subtract off the mean, divide by the standard deviation. It's basically what we were doing at the very, or towards the tail end of class last time. So we can look at a couple of the kind of popular score or possibilities here. The mean height for males aged 20 or older is 69.1 inches. So adult males on average are 69.1 inches tall. That's about 5'9", with a standard deviation of 2.8 inches. The mean height of adult females, basically adult, is 63.7 inches. So about 5 foot, almost 5'4", with a standard deviation of 2.7 inches. So who's relatively taller? So these are two basketball players. You have Kevin Garnett, who played for the Celtics, and he was in the movie Uncut Gems last year. He actually acted in the movie, and he was really good. And then you have, so he was an NBA player, and then you have Candace Parker, a woman. She was in the WNBA, and so she's 76 inches, which is pretty tall for women. Women tend not to get over 6 feet tall, though it is possible. It certainly happens. And then Kevin Garnett is, gosh, what is that? That's literally just under, 7 feet tall? So that's really tall. So what we're going to do is we're going to calculate each of their individual z-scores. So we'll do Garnett's z-score. We'll calculate Candace Parker's z-score as well. And the values we're going to use for Garnett, we're going to use the information concerning males. 69.1 inches on average, standard deviation of 2.8 inches. Remember, here is the z-score formula. It's one that you're basically going to end up ultimately just committing to memory. Let's make that a little straighter. So let's see, Kevin Garnett is 83 inches tall, so that's the X value here. Subtract off the mean, which is 69.1 inches for men, divide by the standard deviation, which for men is 2.8 inches. And so, of course, we're wanting to bust out our handy dandy calculators. And again, if you're whether you're at home on the Zoom or if you're here in person with me, you're going to want to have your calculator pretty much out the rest of the semester, at least available, ready on the quick draw. And so I got mine as well. That's going to be 13.9 on top divided by 2.8, and we're just going to have to, let's say, round to 2 decimal points. Because it's usually, this calculation is not going to come out perfectly clean. So I'll use wavy lines to say, hey, I'm rounding to 2 decimals. 4.96. So here's the skinny on this. Here's the lowdown. Remember, we talked last time, we said there was the empirical rule. And we said that 95, if you have a relatively bell-shaped distribution, which we're going to assume that's the case here, we said 95% of data values fall within 2 standard deviations of the mean. 99.7% of data values fall within 3 standard deviations of the mean. So pretty much almost everyone, if you calculated their z-score would fall between -3 and +3, because the z-score tells you how many standard deviations away from the mean you are. So almost the entire population has a z-score that's somewhere within -3 and +3, and Kevin Garnett's z-score is almost 5. That's mind-blowing. He is incredibly tall for men, for anyone, but even for men, he's incredibly tall. So that's kind of the takeaway here. He has a massive z-score. Let's calculate Candace Parker's z-score. Her height is 76 inches, but we're going to use the mean and standard deviation now for women. For women, so you would do the top first. You do 76 minus 63. And you're going to see that while Candace Parker is still incredibly tall, I mean, for anyone, I mean, 6'4" is a very tall person. No doubt, as Gwen Stefani would say. Her z-score, if you round it to 2 decimal points, her z-score comes out to 4.56. So the overall takeaway here is that Kevin Garnett is not only taller, like he's literally taller. If you put Kevin Garnett next to Candace Parker, Kevin would be taller by what, 7 inches? He's also relatively taller for a man than Candace Parker is for a woman, because even his z-score exceeds Candace Parker's. Now, if somehow you gave me a man who is 80 inches tall, then you might be interested in that. You could say an 80-inch man would still be taller than Candace Parker, but his z-score, I bet, would fall under her z-score, which in that case would mean that she's taller for a woman than person is taller for a man. But Kevin Garnett reigns in both categories. So that's kind of cool. The z-score kind of gives you an apples-to-apples comparison, because it's not fair for me to just compare men against women on average height, because we already know biologically speaking that men are just going to be larger than women. That's just a biological fact. But it is cool that we can put them on their own individual scales and say, okay, but who's taller on their own gender scale? Kind of interesting. Oops. So Kevin Garnett's height was 4.96 standard deviations above the mean. Candace's was 4.56, so Kevin is relatively taller. A boarding school will only admit students who place 1.5 standard deviations above the mean on a standardized test. The test has an average score of 200, so it's one of those weird tests that's like, you know how the SAT is out of 800 on each section? It's just one of those weirdo tests. The test has an average score of 200 and a standard deviation of 26. What is the minimum score to get in? Ooh. So you have to score at least 1.5 standard deviations above the mean. So what this means, your z-score must be at least what? 200 is the average on the entire test. Exactly, but your z-score is the number of standard deviations away from the mean you are. So your z-score must be at least 1.5. And then the mean is 200, so that's going to be our mu. I'll put this down here. That's going to be our mu. And our standard deviation of 26 will be our sigma. So actually now what we're doing is we're solving for x. We're solving for the score on the original scale. That's what x means. X is a data value from the original scale of the data. So in other words, our formula, which is z equal, put it off to the side here, z equals x minus mu over sigma. We know what z is. It's got to be 1.5. We don't know what x is. That's going to be our unknown quantity. But I know that I can subtract off the mean of 200, divide by the standard deviation, which is 26. And so now I got to solve this bad boy for x. So we just rely on our basic algebra. This 26 is multiplying out, so I don't like it. So let's multiply both sides by 26. You're going to get 26 times 1.5 is 39. 39 equals x minus 200. Then we would just need to add 200 to both sides. And you're going to get 239 as your x value. And of course, you can just write that as x equals 239. Let's make a better 2 than that. So I gave you an equation for the z-score, but you could be missing a value. You could be missing a value, and then you're just going to have to solve for that value. So we do got to bring in some of our algebra skills here and there. So the boarding school requires at least a score of 239 on this exam for a student to be admitted to the school. So sometimes we see the z-score formula up here, x minus mu over sigma, but sometimes you'll see that formula, you'll see it solved for x automatically. And so you would just multiply both sides by sigma, add mu, so you'll have x equals mu plus z, your z-score, times sigma. And we could have just straight up used this formula here to solve this one. But just remember, all I did was multiply by sigma, add mu. It's nothing, this is nothing special. This doesn't even need to be memorized per se. Your standard z-score formula, that's the one that's better for you to memorize. If you had to. So z-score is important. We're going to be talking about z-score pretty much now for the rest of this course. We're going to look at it from different perspectives, and we're going to see z-score is something that will not be going away anytime soon. So now what we're going to talk about is percentile. Percentile. Now sometimes you hear like, oh, Texas, or at least Texas used to have this rule when I was going to college. Texas had a rule, a law, that for any Texas public university, they had to automatically accept students who were in the top 10% of their high school graduating class. Have y'all ever heard of that or something similar to that? There was a law in Texas. Basically, if you graduated in the top 10% of your high school class, exactly. Yeah, is that still around? That's still around? Okay, yeah, it was definitely around when I was going to college in the 1930s, as some of you might think about me. That's not true. I'm not that old. Okay. Yeah, some of the schools had to be a little more selective. Of course, with coronavirus, they're probably like, no, please come. We'll pay you to come to college, please. That's not entirely true. But anyways, so if you were in the top 10%, what that meant was that it was entirely based on your GPA, your grade point average. And they would say, okay, you could get in the top 10%. That means your GPA is better than 90% of people. If you were exactly just barely in the top 10%, your GPA was better than 90% of students at the school. So that was an example of a percentile. But what we really do is what we say is the percentile is the percent of people you're above, you're better than. So P98 here, that is whatever score is better than 98% of people. That's what P98 means. P99 is the score that's better than 99% of people. And so on. And so we leave a big gap out here. But P2, that's probably not what you want unless it just so happens, well, no, that's usually not what you want. You don't want to be better than only 2% of people. You'd rather be better than 98%. So percentile is really easy. So if you're just barely snug in the top 10% of your graduating class, that means you were the 90th percentile because you were better than 90% of other people. Does that make sense? Is that pretty straightforward? So whatever the percentile is, Jennifer got a 600 on the math portion of the SAT. Her score is in the 74th percentile. That means, thus, Jennifer scored better than 74% of people on the math SAT, which is pretty good. Pretty good. She was in the top 26%. That's what that means. She was in the top 26% of test takers. That's not bad. Good work, Jennifer. And so that's where things start to get interesting. You might say, oh, well, my average score, or, I beat the average score on this exam by 10 points. Okay, that may not be super interesting because I don't know if 10 points is really good. What if the average score, what if the exam's scale was like 1,000 was the average? Yeah, the average score is 1,000 and you scored a 1,010. That's nice, you were a little bit above average, but that's not entirely telling. That doesn't give me an idea of how far above average you are. That's where z-score comes in. So just knowing the average of a data set doesn't really paint the whole picture. If I can also know the standard deviation of the set, I get an idea of the scale. Well, what if the average score in the exam was 1,000, but for some reason the standard deviation was really small and it was only 2, which is very tiny compared to the mean. But that means if you scored 10 points above the average, you were 5 standard deviations above the average, which is pretty darn impressive, being 5 standard deviations above the average. So it all just depends on what you have. There we go. So we can talk about percentiles. That's where you chop up the graph, basically. You chop up the 100% that's available into basically 100 different pieces. Theoretically, you could say 101, not the Dalmatians. So P1, you're better than 1% of people. P2, okay, that's cool. But what we're going to do instead, more commonly, you talk about quartiles. You talk about quartiles. And what you say is you say, okay, well, instead of dividing it into 100 different pieces, let's divide it into 4 different pieces. You have the bottom 25%, you have the next 25%, you have the next 25%, and then you have the top 25%. And so Q1 is the first quartile, you might call it, aka the 25th percentile. It is the value for which 25% of the data falls below. So Q1 is the first quartile. Then Q2 is the data value for which 50% of the data falls below and 50% falls above. But remember, we already defined that as the median. That was exactly the same thing as the median. It's kind of like the halfway point. It's what half the data falls above, half falls below. So Q2 is just another way of saying median. It's just a different, just according to this definition. Q3 is the third quartile. 75% of the data falls below it. Don't believe me? Well, there's these pieces, 25 plus 25 plus 25. 75% of the data falls below Q3 and 25% falls above it. So Jennifer's score up there was almost at the third quartile. She's just a hair underneath the third quartile. And then finally, the largest data value, that's just the maximum, that's the highest you can go. You can call that Q4 if you really wanted to, because it's, I mean, that's according to this terminology we're adopting. And you could call the smallest data value Q0, Q0. Just depends on your flavor. So quartiles just divide the data set into 4 distinct pieces. You can divide it into as many pieces as you want. What if I wanted to divide it, the 100%, into 10 pieces? Those are called deciles. Your first decile separates the bottom 10% from the top 90%. Then your second decile separates the bottom 20% from the top 80%. The ninth decile, and so on and so forth. So you can do deciles. There's something called the star system. I don't know, I just saw it recently that's being used that splits the graph into 9 pieces. You can split it into 5 easy pieces if you wanted to. You could maybe call those quintiles. So it's really kind of arbitrary. It just so happens that quartiles is kind of just like an industry norm or a standard. It's just what's used, but you can divide it into as many pieces as you want. You divide it into 100 pieces, those are percentiles that we already covered. All right there, Pilgrim. Let's actually see how can we find the quartiles. Well, there's 5 different quartiles that we're interested in. It sounds like there should be 4, but remember we gotta, you just go up here and count. The smallest, if we call that Q0, Q1, Q2, Q3, and Q4, that actually creates 5 total if you think about it. So now, let's talk about how do we find the quartiles. First, you gotta put the data in ascending order, from least to greatest. Then you gotta determine the median. Now the median is going to be really interesting. We already know how to do the median. We've already figured that out in previous lectures. But now we got to find the quartiles. So once you have the median, divide the data set into halves. The observations below the median and the observations above the median. The first quartile is just the median of the bottom half. The third quartile is the median of the top half. So let's see here. A group of BYU Idaho students collected data on the speed of vehicles traveling through a construction zone on a state highway where the posted speed limit was 25 miles per hour. So these students, another word for them is probably narcs. They're trying to narc on people, which is a nice way of saying you rat people out. You tell on other people. You say, you're going too fast. Let me give you a life lesson right now. Let me give you a life lesson. If it's not life or death, if it's just a matter of, oh, should I tell on this person? Don't. You never, ever, 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 ever rat out your friends. Unless they're doing something that's just wildly, horribly illegal, could get people hurt, selling drugs or something ridiculous like that. And even then, that's like, well, if I have feelings about that. You never rat out your friends. You don't. And I know that's not something that an authority figure should be telling you to do, but I firmly believe in that. You don't rat out your friends. They say this, what's that? Yeah, you don't rat your, okay, if your friends are just, I don't want to give specific examples because I don't want to get in trouble, but if your friends are doing something that's not really all that harmful and you're like, oh, I'm going to go tell their parents, come on, just don't rat your friends out. That is a quick way to becoming unpopular. And being unpopular is not a good thing. Being popular, having good social skills, is a far better indicator of success than anything else. I'm serious. Having good social skills. Yeah, exactly. Like it's connections, it's people. And if you get a reputation for being a rat, nobody wants you. Nobody's going to want to hire you or help you get a job if they're your buddy. So you don't rat your friends out. They say there's two things, and this is from a mob movie, and of course the mob is terrible. Mob movies are the best. You don't rat your friends out in the mob. Exactly. They call them rats. He's broadcasting on WRAT. You don't rat your friends out. And in the mob movies, they'll say, if you ever get pinched, if you ever get brought in for questioning or something, you do two things. You don't tell them anything, and you always keep your mouth shut. So I'm also saying this a little tongue in cheek. It's a little bit of fun. We're just having fun here. But I do believe you don't rat your friends out. Anywho, okay, but there's exceptions. If your friend committed a murder and is going to continue doing that, look, there's other lives involved. But if it's just something silly, like obviously you can't promote murder. So I'm talking about just kind of simpler things that could get them in trouble or grounded, especially if you're in like middle school, high school. And they're like, oh, he punched a kid at school. And, just there's things that aren't that big a deal. So anyways, these 4 students who are ratting out other drivers in the university, they collected the speeds that 14 randomly selected vehicles were driving in a certain speed zone. So the data's already been put in order for you. That's awesome. But it probably wasn't collected in this order. It's very unlikely that it just so happened to be in order when they collected. So they probably collected like the 33 first, then they got the 28 mile an hour driver, then the 40, then the 24, then the 34. So the data's just already happened to be put in order for you. Now, what you can see, the first thing we got to do is calculate the median. In fact, actually, what we're going to do is we're going to calculate Q0, and technically there should be a subscript, so I guess I'll write it out. We'll do Q0, Q1, the first quartile, Q2, the median or second quartile, Q3, the third quartile, and Q4, the fourth quartile, which we're just going to say is the maximum value. Now, what we see is that we got to put the data from least to greatest first, which just so happens to have already been given to you. If this data wasn't given to you in least to greatest, what would you need to do? Exactly. Do it yourself. Yeah, order it. Put it in least to greatest. Exactly. But it just so happens to do that. And once you do that, these first two, the Q0 and the Q4 values are right there. They're handed to you. 20 and 40. Next, we'll go ahead and calculate the median. And there's a couple ways we can do it. We can do our cross-out method, but that's almost a bit primitive. So instead, let's do it a slightly different way. Remember, there's 14 total vehicles or speeds here that have been collected, 14 data values, which means there's not going to be a value that's perfectly in the middle. There's going to be 2 that share the middle. So let's see, 1, 2, 3, 4, 5, 6, 7. So this right here separates the bottom half and the top half. Now, if you did have an odd number of data values, let's say we added a 42, Jackie Robinson's number. Let's say we added a 42, then there would be a data value perfectly in the middle, and it would be this 33. So if this were the data set, the median would be 33, and we're playing what if. Then you divide it into the bottom half and the top half, and you basically, if there's an odd number of data values, you ignore the very middle value. And so what you would do is you would say, this is your bottom half. This is your top half. So bottom half, top half. That's what you would do if you had an odd number of data values. You'd get the median, but then you ignore the median when you split it into halves. However, that's not the issue we have here. Remember, we don't have an odd number of data values. We truly have an even number of data values. So you go back over here, and you go back to splitting it into top half, bottom half. Now the median is going to be somewhere between the 32 and the 33. So remember, you take the average of those 2 numbers in the middle, but you can probably see that you're just splitting the difference between them, and it's going to be 32.5. Is going to be your median. And now once you see that, now you've already separated it into top half, bottom half, and you're doing the same thing as before. You're not including the median because the median was in between the 32 and 33. So here's the bottom half, here's the top half. And so now to find the quartiles, you find the median of the bottom half, that'll be your first quartile. So let's see, there's 1, 2, 3, 4, 5, 6, 7 data values in the bottom half. So now maybe you can use your cross-out method if that is your fancy. You know you're going to have something, there it is. And that'll be your first quartile. Makes sense too. Now for your third quartile, you take the median of the top half. You know there's 7 data values in the top half. So we know there's going to be something perfectly in the middle. Sometimes that's called the Malcolm. And so we know 38 is going to be the third quartile. And then I wish there was a way to copy paste. Let's see. That witchcraft is not identified here. It's not allowed. So I'm just gonna take a quick picture of it and I'll refer. I would write down the quartiles here on your own paper, on your own work, because I'm just gonna refer back to it, but I'm gonna have to erase it, and Zoom's system doesn't have a very easy way of just recalling stuff. Not without a little bit of pain. And so there you go. So interpret the quartiles. Well, Q0 and Q4 are, okay, you can do it. Q0 is just the smallest possible value, and that's the value that is better than nothing else. It's higher than nothing else. Q4 is the value that is better than everything else. It's better than 100% or all four quartiles. Q1 is the first quartile. It's better than 25% of the data. Q3 is better than 75% of the data. The median is better than 50% of the data. Probably heard my tummy rumbling because all I had was a stupid Fiber One bar because I'm trying to lose weight because I put on some weight during the coronavirus, and that was very easy to do. I used to go to the gym 4 times a week. I loved going to the gym 4 times a week. Yeah, after about 3 weeks, it sucks for 3 weeks, but then if you're taking your protein shakes, you're drinking your pre-workout, I even drank something during the workout. If you're doing all that, you'll never be sore again, and you can push yourself hard and not be sore, seriously. And you get into the routine of it, it's not so bad, it's fun. I would watch things, listen to audiobooks, listen specifically to Star Wars audiobooks while I was doing my cardio at the beginning. I loved it. Then the coronavirus hit and all the gyms shut down and Whataburger didn't shut down. And I said, I have a testimony to eat a lot of Whataburger and not go to the gym, all right? That's how I felt. Yeah, I still feel like that. Yeah, it's like, I don't know if I should go to the gym now even. So anyways, what we're going to see is that this is going to be called the 5-number summary. That's a very terse title for it. There's 5 values: the minimum, the first quartile, second quartile / median, third quartile, and the maximum. The 5-number summary. And what we'll see likely next time is that we're going to deal with something called a box plot. And that's going to be a visual representation of the 5-number summary. And we'll do that next time, but we still have more in this section. Okay, so remember that 5-number summary, because it's now gone. In an UMBOP, it is gone. Real quick, let's take attendance so that I do not forget. Mary Lee is right here. And you are Ryan Goodwin. And you are Tira. Very good. And then, yeah, just go ahead in the Zoom room and type your name out for me. So Kara, hello Kara, how are you today? Kara has been counted present. Brooklyn, you are also being counted present. I'm glad to see that you're great, Kara. That makes me happy. I've got nothing but good vibrations, good things I want from my students. So I'll go ahead and pause the recording real quick so that people watching on the YouTube later don't have to waste their time with this. Back to it. Okay, the next concept that we're going to talk about is something called the interquartile range. And even though it's kind of has a lot of syllables, it is the most rock simple thing on the planet. The interquartile range, the first and third quartiles, let's go look at that picture again. The first quartile and the third quartile, they feel like the inside ones. They're inner, and we're just taking the range. A range is just a difference between a smaller and a larger value, usually. So the interquartile range is literally just Q3 minus Q1. And it just ain't a lick more difficult than that. That's it. That's it. What it does is it tells you the range of the middle 50% of the values. Oh, the middle 50% of things fall between, I believe it was 28 and 38 for that speed data, if you remember. So the middle 50% of values range within 10 units from each other. They're all within 10 units of each other. So we'll calculate that real quick. For the speed data, not the movie with Sandra Bullock and Keanu Reeves, or the vastly inferior sequel, you'll remember that Q1 for the speed data was 28, Q3 was 38, and now I shall apply my wizardry. and compute the IQR, the the inner quartile range. And look at that, it's just 10. Really, I'm not kidding. It's not a lick more complicated than that. It's the range of the middle 50%. In other words, if you're in the middle 50%, you at most are 10 units or 10 miles an hour different from anything else in the middle 50%. That's the highest it can go. And so the range of the middle 50% of the data traveling through the construction zone is 10 miles per hour. Now, wait a minute, Josh, you say. The interquartile range was rock simple. Did that break anyone's brains to find that? No, I don't think so. You just take Q3 minus Q1. So in order to find it, you pretty much already have to do the 5-number summary. You kind of have to start off with that. But once you found it, we're actually going to utilize the interquartile range to determine if something is an outlier, if something is a very, very large value. So earlier we had, and I apologize. So again, the interquartile range was just for that speed data, 38 minus 28. So 10. Now, let's suppose earlier we had 14 data values. These 14 drivers, and they're all reasonably within, 20 to 40 miles an hour is not that big a difference at the end of the day. But let's say you had some maniac get out on the road driving 100 miles an hour. And remember, the speed limit was 25. And this person is driving 100. Maybe it's a 16-year-old who just got their first car, or maybe it's a 16-year-old who's trying to impress their girlfriend, or maybe it's a 16-year-old who's trying to impress his friends. Hint and a wink, it's going to be a male who is young that is going to be driving that much, because we all know men tend to be a little more reckless, and that's, in that case, that's not okay. And if you see someone going 100 miles an hour, you might need to rat them out, because that's like a severe public, even on the highway, that's ridiculous. But in a 25-mile-an-hour speed zone, I mean, that's just ridiculously unsafe. But here's how that affects it. Before, if you just looked at the 14 cars, we've calculated some statistics for you there. Just looking at the 14 cars, their average, their mean speed, which we did not calculate ourselves, was 32.1 miles an hour. Their median was 32.5 miles an hour. And then the standard deviation, which we did not compute, happened to be 6.2, and the interquartile range was 10. If you throw the 15th car in there, if you take this data and you throw the 15th car, which was going 100 miles per hour, just absolutely unsafe speeds, this is how the data would be affected by that. Your mean would go up a good chunk. It goes up by, almost 5 miles an hour, the average goes up. The median barely goes up, which makes sense. If you throw 100 here at the end, then all that does is slightly move the median to the 33 to be in the middle. So that's, again, that's what we were talking about last time and a few times ago concerning resistance. The mean is not very resistant to outliers. If you put a hilariously large value in there, and also that value is something that's worth looking at. It's not something we just ignore. Oh, that's too large, we ignore it. No, if someone's driving 100 miles an hour through there when you're taking your data, maybe that's something that's worth considering. So we can't just always throw it out for no good reason. But notice the mean went up by a lot. The median barely moved. It went bloop. It barely moved on the thing. The standard deviation went up a hilarious amount, ridiculous amount. The standard deviation was 6.2 miles an hour. Now it's 18.5 miles an hour. Get out of here. Remember, the standard deviation, what it does is it gives us an idea of how spread out the data values are. The larger your standard deviation, the more spread out your data is. So if you're jumping from 6.2 to 18.5, Now this data is much more spread out, or so it appears to be. So here's the thing. If you have a symmetric data set, if you have something that follows a nice bell curve and it behaves appropriately, the best measure of central tendency to use is the mean. And the best measure of dispersion of how much the data values spread out is the standard deviation. And in fact, that's going to be the usual tactic we employ. We use the mean and standard deviation. But if your data has any outliers, if your data is skewed left or right, the median is going to be a better measure of central tendency. The interquartile range, the IQR, is actually your better measure of dispersion, at least at a fairly elementary level. Now you can go above and beyond that, but you know. So here's what we're going to do. We're going to check for outliers by using quartiles. You're going to, what you do, well, maybe I won't go super detailed with the explanation, but basically you're going to use what we call this fences method. Fences, not the, is it a Robert Frost poem, Fences? Not the Robert Frost poem. What you're going to do is you're going to use, first of all, you got to compute the 5-number summary for your data. You got to know the min, the max, the median, but most importantly, you got to know what Q1 and Q3 are. So let's remind ourselves the speed data of just the 14 cars. Let's say just the 14 cars. The speed data, it was, the first quartile was 28 miles an hour. The third quartile was 38 miles an hour. So the IQR was very simple. It was 10 miles an hour. The range of the two inner quartiles. Now what you're going to do is you're going to compute something called the fences. And the fences are going to give you the boundaries. If a data value is inside the fences, it's okay. It's not an outlier. If a data value is outside the fences, if it's larger than the upper fence or smaller than the lower fence, it is going to be something we identify as an outlier. And what do we do with outliers? And that's actually kind of debatable. You can't always just throw them out willy-nilly. You have to really look at them and consider them. But outliers are worth discovering. They're worth looking at. So what we're going to do, I will use my magics. Is he a magician? Yes. We're going to compute the fences. The lower fence is found by taking the first quartile, not the minimum, the first quartile, and subtracting off 1.5 times the IQR. So it's going to be 28 was the first quartile, minus 1.5 times the IQR was 10. Of course, you have calculators. That becomes 28 minus 15, which is just 13. You're going to compute the upper fence. You're going to take the third quartile, which was 38, and add 1.5 times the IQR. The IQR is still 10. $38 plus 15, my mental math tells me that's 53. And now, these fences tell you, if a data value is inside the fences, if it's somewhere between 13 and 53, if it happens to be equal to one of the fences, that's fine. It's still going to be a valid value. So, all data values between 13 and 15, and if you like using interval notation from algebra, I'm sorry, 13 and 53, excuse me. I don't know why 15 came on my mind. If you use interval notation, that's 13 comma 53, and then you use brackets on either end. That means you can include the 13 and the 53. So if the data value is 17, that's inside the brackets. It's inside 13. If a data value is exactly 13, that's still okay. It's the smallest possible value you're allowed to be, but you're still not an outlier. So all data values between 13 and 53 are not outliers. Anything outside this is considered an outlier. And that doesn't mean we take it to the public square and we execute it and we throw it out of the data set. That just means this is a moment for us to pause, look at it carefully, analyze it. Hey, maybe we had a data collection error. Maybe we were collecting blood pressures and we got a reading of 1500 for your blood pressure. That's clearly a mistake happened. So that's the point of looking for outliers, is to decide, was there a mistake? Or is this a legitimate recording? Is this a legitimate data value we recorded? And there's nothing you can do about it. It's just part of the data set and it's valid. So that's what that means. So we go back to, there it is. There's the speed data, 20 to 40. Is everything inside the fences? Yeah, 20. The lowest you can go is still well above the 13. So the 13 and the 53, the fences, are not always going to be data values themselves. And they could also be, you could have gotten a negative number for the lower fence, even though none of these could have gone negative. That's okay. That's just saying the lower fence is really, really low. The upper fence is 53. And the highest the data values go is 40. So there's no outliers here. No outliers. Everything behaves, everything exists within the fences. However, let's play pretend. And now let's throw in that 16-year-old trying to impress his friends or his girlfriend. Let's throw in that young, reckless person who's going 100 miles an hour. And it's, 25 miles an hour, that's even slower than some neighborhoods. Like calm, peaceful neighborhoods will still have a speed limit of 30. A 25 is like you're near a school or you're driving by a school, but it just, and they'll even lower that speed during school hours. But even outside of school hours, they don't want people driving crazily near them. So if you're going 100, like near a school, come on. Okay, you deserve to be narked on. That's just, you're asking for it. But anyways, 100 miles an hour. Now here's the thing, if I add that 100 miles an hour, that creates a little bit of an issue because that actually does change my 5-number summary. That moves the median up slightly from 32.5 to 33. That's actually also going to have a possibility of changing the first and third quartiles. In fact, it will change at least the third quartile. So just adding that extra value in does technically change these calculations just a little bit. So instead of just throwing 100 in there, let's say that last observation was, instead of being someone else driving 40, let's say the last observation was 100, and you still have 14 total data values, just so we don't have to recalculate. The only thing that would change in the 5-number summary then is the maximum value. But the median, the first quartile, third quartile, interquartile range, the fences would all be exactly the same. And now what we can see is, oh yeah, that 100 is way above the upper fence of 53. So now, if this were the case, we'd say 100 is definitely an outlier. Similarly, so that's that case. If you replaced the 20 with, how about someone was going 5 miles an hour? Maybe they're having car issues, something like that. So we still have 14 total values. The 5-number summary almost stays the same, except technically the minimum value now switches to 5. But the first, second, and third quartiles and the maximum all stay the same. So the interquartile range stays the same, and the fences stay the same. Now, would 5 be an outlier here? Bet your bottom dollar it would there, Pilgrim. Yeah, that 5 is definitely an outlier here.